Alright, so hello everyone, my name is Viraj and today we'll be discussing the contest problems from Biweekly 157 from Leetcode. We'll be discussing all the 4 problems. Today's contest was a little bit easier and straightforwardly educational, I would say. And yeah, let's start. So I'll be moving on first of all to discuss the TLE Eliminators channel and our courses, our mentors, which bring you this PCDs every day for Leetcode, Code Chef, and Code Forces. We have 4 levels at TLE where we cover topics right from the scratch of starting your world in CP to a very high level till going to topics like dynamic programming, segment trees, and graphs. So make sure you check this out. Besides that, we have a very curated CP sheet, TLE CP sheet 31, where we have problem sets right from 800 to 1900, along with which, of course, the post-contest discussions that you see every day on the channel. So make sure you check out these courses, and if you're someone who is looking out to start in this CP paradigm, make sure that TLE is something you definitely check out. All right, so let's move on quickly. Let's go on to the first problem that came today. It has a medium tag. It does not have an easy tag, but then the problem itself is very, you can say, straightforward and implementative. Let's try to read this. Given a string S, find the sum of the 3 largest unique prime numbers that are formed using any of its substrings. Return the sum of these 3 largest unique prime numbers that can be formed. If there are fewer than 3, then return the sum of all available primes. If there is no prime, then of course return 0. By common sense, this makes sense. All right. Now, what is a prime number? For any beginner out there, a prime number is a natural number greater than 1, which has only 2 factors, 1 in itself. Naturally, you can imagine 2, 3, 5, 7, all these list of numbers to be prime. Okay, no explanation there. A substring is a continuous sequence of characters within a string. Now note, each prime number should be counted only once, even if it appears in multiple strings or substrings rather. Additionally, when converting a substring to an integer, any leading zeros are ignored. Okay, so I hope the problem itself makes sense. Let's quickly try to discuss a very simple analogy in this problem. What are they saying? They say that they will give you a string S, okay? It is going to have the numbers in it. So for example, I take 1, 1, 2, and 4, and what have they given more? Okay, so this is 1, 1, 2, 3, and 4. Okay, now you can extract these substrings from this. Now what does a substring mean? Basically, start from some point, end at some point, that's a substring. So maybe I pick up these 2 letters together, that's a substring. This much, 1, 2, 3, it's a substring. I pick up this much, 3, 4, it's a substring. So I would be able to pick up all the substrings from this particular string. They have actually noted down the substrings that normally we can form. And in these substrings, since they are itself, you can imagine to be a number, you can convert these substrings to an integer, or rather a number. If there are any leading zeros, that means if the number or rather the substring looks like this, 0, 0, 1, then this actually is simply written as 1 because these 2 zeros are leading zeros. So I don't want them. I'll say that when I convert all the substrings from the string, okay, all the substrings from this string to an integer, and I then consider only the unique integers in this, then all those integers which are prime in nature, I have to take the top 3 prime and return their sum. For example, in this case, you can say that the unique integers, or effectively unique prime, turned out to be 2, 3, 23, 2, 2, 3, and 1, 2, 2, 3. You can of course pause the video and check this out. And if you take the top 3 primes, that is basically 1, 2, 2, 3, 2, 2, 3, and 2, 3, so you basically return a sum to be 1, 4, 6, 9, and that's your answer. Now let's say I would talk about test case number 2. The unique prime number formed over here is just a single number 11. Now, they have very neatly said that it is not necessary you always have 3 unique numbers or 3 unique prime numbers rather. It might happen you will have less than them. So it's okay. Just take their sum and that's going to be the answer. I can say that the answer is just 11 and I'll print 11. Had there been no prime numbers found, then I would have returned 0. Okay, so very straight, very simple problem to understand. Now, why is it rated medium as a tag for any beginner who might be thinking? It's about the implementation over here, right? If you understand the problem, you should now try to understand that if I go towards the implementation, I should actually see what's the constraints. And when I look at the constraints, I can see that s.length is actually very, very small. It's barely going to a max length of 10. Now, when this small set of constraints are looked upon, your mind should of course run towards a very brute force solution. If I actually do what is required, that is, if I actually try to find all the substrings, convert them to an integer, maybe figure out the unique ones, and check for their primality, can I do all of this considering that s.length is maximum going till 10? Can I do that? Pause the video and think yourself. Yes, I actually can. This is the beauty of this problem. This is why it's just medium rated. It's not that hard. I just need to figure out and revise all the concepts I know to check a prime, to extract a substring, to maybe maintain them in some sort of a data set which gives me uniqueness, and at the very end, print the top 3 as a sum. That's all. If I'm able to do that, then I know I've solved the problem. Okay, so how do we do this exactly? Any small revision over here is required of finding the substrings, probably primality testing, so I'll write it over here. How do you find a substring? Okay, how do you find each substring? Okay, how do you find each substring? This is of course required. Then of course it's required that how do you check for primes? How do you check for primes? And then of course some data set or some data type rather, which basically allows you to maintain uniqueness in it. Okay, unique datas in it. Okay, so if these 3 things are something you know, you have solved the problem. Let's actually move on to a very small pseudocode of how I would be doing this. So first of all, I need a data set which maintains uniqueness. Just out of the blue, it's very obvious I can use a set. Okay, I can use a set of, let's say, called S. It's the integer type because I want unique integers. The next thing that I want is I need to find every substring. So I have length as n. I can store it as s.length n. Okay. Now I want to extract every substring's size. So how do I do that part? I can run some sort of an outer for loop, which basically tells me that, okay, what is the start of each substring? So this is going to be index I. It, let's say, starts from 0 and goes on to the n-1 index. And then inside this, I can have another for loop, which basically tells me, okay, what is going to be the end of my substring? So end of my substrings means this is j, let's say, it basically starts with I, let's say, and it goes right up to the end, that is n-1. Now what I have is 2 variables which control the start and the end of what can be the 2 positions between which I want the string to be extracted, that substring. So I can simply call the s.substr function, and I can say something that starts from the index I, and how much length do I want? That's basically j minus I plus 1. Give it a thought. It's a very basic thing. You basically are considering the length, that is j minus I plus 1. That is the length of the current substring that you want. And when you extract this, then you basically want to convert this to an integer. Remember, this is a substring. So now it's a very simple C++ sort of an STL function that I'll be calling over here. I know that as STOLL, or there is actually one function that is also called STOI, that is string to integer or string to long. Now in this case, because I'm just making sure that I don't go any sort of overflow or underflow, any sort of that condition, so I'm just using STOLL function. So what I'll do is, after I've extracted this substring, I can just pass it to the STOLL function, and this will return to me that number that I'm talking about. And that number can then be inserted, like insert this in S. That's the set. And voila, this is my overall code to actually finding the strings and actually inserting them back in the set. Now, over here, what I can do actually is, I think I missed this point. Before you actually want to insert in S, you also want to check whether the number that you just got, is it a prime or not? Now, to do that, you can have a very simple primality testing method, sort of a function made out of this pseudocode. You can create it outside the main function, and you can call it as a utility. That primality test can be any popular method you know of. You can Google this out also to check for a prime number. Now, one of the best methods that I know is actually called as the square root method. Okay, where we basically end up running a loop that runs from, let's say, I equals to 1 to I is less than square root of n, and this is like I plus plus, and then I end up checking whether the number has any factors or not. If it does have any factors, that means I know it's not a prime, of course, except 1 and n itself, any other thing, that's very, very obvious. But else, if it does not return any factor beside 1 and n itself, then I know it's a prime number. So why does this idea work, and why do we run a loop till root of n? Some hint is of course given by square root method. You can pause the video and actually search this method, and you will actually understand why do we do this by root of n. I'll give you a small hint over here only. This is because factors of a number actually come in pairs. And because they come in pairs, it's very easy for me to not iterate till the very n number itself, but rather a root of that number is more than enough to check for its factors. Okay, so this is the idea. So I'll be calling this some sort of a very popular square root method over here to check whether the number which I insert in S, is it prime or not. I can check it. If it returns true, only then I insert it, else I don't insert it. Okay, so this pseudo part is done. And when you end this whole for loop structure along with the primality testing and everything, you have a very neat set filled with the numbers which are prime. And of course, they are unique because you know you have taken a simple set. So it's going to maintain and numbers in a unique manner. It does not have any duplicacy. Then all you want is how do you take the top 3 values in the set. For that, very neat thing that we can do. Now, because this is a set, remember you cannot iterate on this set normally like you do in a vector and an array. You would want some sort of a iterator from where you start and where you end. Now, because this set is going to have the order as increasing, okay, the values are going to be stored in increasing order, and I want them to be calculated from decreasing because I want them to calculate from the back. So I would want that I have some sort of an auto it, that's the iterator, which actually starts with the back of this particular set. How do I call that? I can say s.r begin. This is basically the reverse from the back hand side, or r begin is reverse from begin. And I can say something like till it is not equal to s.r end, and till until this doesn't happen, I can actually go on to each and every value, and using that value, and I can actually pick it up and make my answer go by that value high. Okay, that's basically calculating a very simple sum. And maybe I can have one more variable which tells me how many values have I picked so far. Okay, how many values have I picked so far? So if I have picked 3 values, I know I will break. Very simple. I'll say if picked has become equal to 3, I would want to break. Okay, and of course there is a sum variable which is getting added with this it variable. Now, why again am I stressing this is a medium question? Because of all these parts, right? You understand that there is an STL involved. You might not know the best way to actually iterate on a set in this manner. Maybe you don't know how to calculate a substring, or maybe you're not aware of this square root method. So these are not beginner concepts, but they're not even advanced concepts. These are very intermediate concepts, which if you know, this problem is solved because the logic is barely a cakewalk. Okay, so hence this is the whole problem solution. Let us move on to the coding part, and you will see this in motion. Okay, so as you can see, first of all, the is prime function. This is again a very small function I have written. You can rip it off from anywhere. Simply checks prime by the square root method testing. If n is less than 2, then I know n is prime, so I'll return a false directly. Then I have this square root testing. D is 2. D into d is less than equal to n, or basically that means d is less than equal to root of n. Now, if n mod d is 0, that means d is a factor. And because d starts with 2, then I know I have actually landed at a number which is a factor of n. So I know n is no longer a prime, so I'll return false. But if I don't actually do anything over here, I return a true, which tells me that yes, n was a prime in nature. Now the main code over here, you have the set long primes. Then you basically would want that you are able to iterate in this outer for loop of I, and then the inner for loop of j, as I explained. Then the number is basically stoll called by s.substr from ij minus I plus 1. So this extracts the substring and then converts it. Then you basically pass this number to the is prime function, and if it does return true, you insert it in the primes set. Now, once you complete this, you have a set neatly established, made up of all the values required, and then you have the answer, that's the sum you want to print, and the picked. You basically iterate from the back in this set, and you do that till picked is less than 3. If you know you are going inside this loop, you're taking the largest value and you're adding it to answer. By the way, you want to dereference it because it's an iterator, so putting a star will get you that value, and picked becomes ++. So this loop basically runs till picked is less than 3, and as soon as it crosses 3, you break. So if it's less than 3 numbers actually in value, then you only take their sum. Even it's more than 3 numbers, then you take the top 3 automatically. This should be very, very simple. And then you return the answer. All right, so this runs on all the cases. Now what is the time complexity over here? This is pretty much n order. Now I'm considering n to be the size of this string that I'm talking about. This is n order again. And then this substring extraction is also in n order, although this prime logic is something different. See, over here when you're converting the number which has a 10 size overall, then that means some sort of a 10 power 10 is an order which you will be passing in this prime function. But this runs in square root method, and square root method actually has a root of the number that you pass inside this as the complexity. So this function actually boils down to 10 power 10 root, that is 10 power 5. Now if I actually write what's the time complexity for this overall, this is n into this is 10 power 5 order. Now n was 10 maximum, so this is also 10 and this is also 10, which means you have actually come up with something like 10 power 7 order approximately, I should say. That is not wrong, and you can of course comment down in the chat and let me know if you think this is right. And this is, I think, the pretty much largest complexity piece that will pop up, because this is not going to be very high. Maximum substrings are going to be barely, I can say, 50 to 60 substrings. So I know that this is not going to be a very high loop. Again, this is the very upper bound that I've taken. This is not exactly n into n, but rather because the loop starts with I, so this is a little lesser than that. But I'll leave that to the chat and you can let me know what is the exact time complexity that you think. But for now, I think this is good to go. I can write this complexity to be 10 power 7 order, okay? And what about the space complexity? Space complexity is solely dependent over here on this set of primes that we are taking and the string itself. That's a 10 order maximum, and primes are, as I said, you will not gain more than like 60-70 prime numbers of the all possible cases. So I can say this to be some sort of 100 order. That's max. That's the maximum set that I would be gaining. So this is not a big deal anymore, and I can see very clearly that yes, a brute solution did work. So via medium, because of just of these intermediate concepts, but overall a cakewalk problem. Okay, I hope this helps. This is problem number 1. Let us move on to the next problem. All right, problem number 2. You are given a string word. Return the maximum number of non-intersecting substrings of the word that are at least 4 characters long and start and end with the same letter. Okay, a string is a continuous non-empty sequence of characters within a string. Okay, sorry, a substring rather. So sorry, is a continuous non-empty sequence of characters within a string. So we just learned substring in the problem number 1. I hope this is clear. Let's look at the case and understand what are they saying. So something that looks like A, B, C, D, E, A, F, D, E, F, the answer is actually 2, which means there are 2 substrings which are non-intersecting in this, and they start and end at the same letter, and they have at least 4 size. Let's see. A, B, C, D, E, A starts at A, ends at A, has 6 size, which is of course greater than 4, and the other string is FDEF, which starts with F, ends with F, is at least 4 size, exactly 4 in this case, which is greater than equal to 4, and these 2 substrings do not actually intersect. See, this is this much substring, and this is this other portion, so they don't intersect. So I know that the answer is 2. The maximum number of non-intersecting substrings I can actually create with these conditions fulfilled is 2. If I go to example number 2, I can see that this answer is only 1. Why? Very neatly they have actually told you. Sometimes it's very, very beneficial to actually understand the case as well. So one substring you can actually create is A. It starts at A, ends at A, and has 4 size, at least 4 size. The other string, although you can see, is this B, C, D, A, B. This also starts at B, ends at B, but you actually cannot count this. Why? Because this string and this string are intersecting. And because they're intersecting, that means I actually cannot use this to be one of those strings or count them as separate basically. They're intersecting, so I can only count either this or this. That's why the answer is 1. So I want the maximum number of non-intersecting substrings. I don't need to print the substrings. Again, remember, very, very crucial point. I just need to output that number which I feel is the largest. Okay, and as per the constraints, word.length is not very low. It's 2 into 10 raised to 5 order, which means you will not be able to have any sort of a problem solution where you actually end up calculating the substrings. That is going to be really, really high. You need some sort of a solution to this problem where you actually don't end up counting these substrings, but rather something very smart. Okay, so I hope the problem is clear, the cases are clear. Let's quickly jot down our observations and start solving this problem. So first of all, the most important thing that I want is basically start and end at same character. Okay, this is one thing that I want. Okay, great. The other thing that I want is the length to be greater than equal to 4. As in this substring that I extract should have a greater than equal to 4 length. Now the string that is given to me will have different types of characters in it, right? To be specific, characters from A to Z are going to be there, only lowercase English letters. Now, don't you think that it's very neat for me to first of all understand that if I have to fulfill condition number 1, I am only bothered with each and every letter's occurrence at one moment of time. As in, if let's say the string is looking something like this, okay, some letters are there, and let's say there is an A over here, let's say there is an A over here, let's say there is an A over here. So don't you think the substring that I'm actually bothered with, if I say that the start and end is A, then this is this string and then this string. These are the two strings that I'm bothered with. Or the other string that I'm bothered with is actually this third string. So did you see I can actually make 3 strings which actually will start and end at A? Yes, you can see. Now, condition 1 is true, but it might not be necessary that this string that I just pointed out, maybe it does not have a length enough. It does not have a length greater than equal to 4. So maybe I would have to drop that substring, not take that, or maybe some other substring. It can happen, right? But the first condition to be satisfied tells me that you need to first of all find the occurrences of every letter. I need these indexes. I need, let's say if I'm talking about the letter A, then I need to know where is A placed. If let's say I was talking about B, then I need to know where is the letter B placed, where is the letter C placed. And only then I can work in those particular indexes. Which means my first hand intuition is just to make sure the condition 1 is satisfied, I need to work with all the 26 letters independently, and I need their indices where all they occur. So for A, I would be trying to figure out where does A occur. Let's say it occurs at I1, I2, I3, maybe it occurs at I7, and so on, so on, so on. Then I would try to figure out where B occurs, where C occurs, all the way up to where does Z occur. Okay, now once I figured out where all they occur, what is my next step? Let's see independence over here. So I'll remove these letters over here and let's just talk about A. So I have, let's say, some random indices which I calculated, and I said, okay, these are the all places where A occurs in the string. Let's move to the first index, that is I1. Okay, let's see I1. So now I1 is an index. You know that if you want a substring to be ending at A, you know you have decided a start, right? You have decided a start. Where do I want this start to have? This is I1. But what is the end? End can be I2, end can be I3, end can be I7, end can be all the other indices where A comes. But do you actually want all the indices? Think greedily over here. Let's go back to the problem and see a very important word. See, this is saying maximum number of non-intersecting substrings. Okay, let's pause this over here and let's go on this one idea very simply. Imagine that you have a stick with you. Okay, this is a stick with you. Now, if you want more number of pieces from this stick, then it's very obvious that you would want to divide this into single pieces which are lesser in length. Let's say if I make 1, 2, 3 and 4 pieces, then every piece has lower length, but then the overall count is 4. On the other hand, if I would have said that make only 2 pieces, then the every piece's length would be high, but the number overall is 2. You only get 2 pieces out of this. You overall are getting 4 pieces out of this. The overall length is a little lower, but overall the length is a little larger. So can you see a proportion, simple sort of a mathematical proportion here? The larger every substring you have, the lesser overall substrings can you make, because you want non-intersection. So same idea over here. If you actually make I1 to be your start, do you want to pick up an index which is like very far away? Something like, let's say I9, I1 to I9. No, right? I don't want that, because that is making my string very large. I want the substring to be very small so that I have more pieces extracted. That means I1 has to be paired with the just right guy, which actually satisfies L greater than equal to 4 position, or sorry, length, 4 length, which means I need to pair I1 with an index from this particular array, which is just greater than I plus 3 in value. Okay, example, if let's say I is an index was 2, then if I plus 3 basically means 5, you're basically looking for the first index in this index's vector which is greater than greater than 5. Now if let's say that first index is 7, then you know that you can pair 2 with 7, and that will end up with a length greater than equal to 4, and that will be a substring that starts with this 2 index, maybe ends at the 7th index, and yes, it is correct. It is starting with A, ending with A, has a greater than equal to 4 size. So this means for I1, I need to figure out this just greater than I plus 3 guy. Similarly, I would want to figure out that for I2, I3, I7, whatever are the indexes 1 and 1 and 1 and so on in this particular vector of indices where A occur, you can call that very simply. I need to figure out this guy which pairs up with it. And that together can be known as some sort of a segment that I've created. I'm basically saying that this is L and this is R. This is an L to R segment that I've marked off where I know this substring is correct. It satisfies both these conditions. It is also starting and ending with the same letter. In this case, I was talking about A, and it also has a size greater than equal to 4. Okay, so I'll be doing this for A. Similarly, I'll be doing this for B, C, D, E, so on till Z. And eventually I will end up with a lot of intervals. I will have some interval that looks like L1 to R1, some interval that's L2 to R2, that's L3 to you can say R3, and so on, so on, so on. You have, let's say, some like LZ to RZ. You have a lot of intervals which will come from all the different letters also, right? And now these can be intersecting also, right? This is just a segment that's marked from L1 to R1, which says that this substring is nice. This is also a segment, but maybe they intersect. Maybe this is L1 to R1, maybe this is L2 to R2. So these intersect, right? These intersected over there. I don't want that. So right now I have just solved like sort of a sub part of the first part of the problem where I figured out what are those segments. I'll write it over here. What are those segments which have a good substring? Okay, when I say good substring means starts and ends at the same letter and of course has greater than equal to 4 length. Now I have greedily also made sure that these segments are the best possibly lowest segments when I'm talking about any particular index. And I did that because I used this thing. Now once I've done this part, you have now encountered or created yourself another sub problem, which is now you have some segments over here. You have to find the largest number of non-intersecting segments from this, and that is your answer. Now how do I find this? This is another very clever problem. It's sort of like a 2-pointer problem, I should say. But what you can do over here now is you can, if let's say these segments are stored in some sort of a vector of pair of int comma int, okay, something like this, then what do? I can basically push, of course, all these segments in this vector, and then I can sort this vector. Okay, I can sort this vector. Okay, and how do I sort this? The ideal way would be to sort, first of all, of course, on the first value. Okay, first value, that is L, and if L is equal for any two pairs, then I would want them to be sorted on their second value. And what sort of a sort I want? What sort of a sort am I looking for? I am looking for a sort where I am able to sort this on the lowest second value first. Okay, lowest second value first. Why lowest second value? Because I want smaller segments more. If I have lower number of smaller segments more, then I know I'll be able to make larger overall count of segments which are non-intersecting. This is the greedy idea. Okay, this is actually a very standard sort. If you just call this on this vector of pair of int comma int, that is what is going to return. And after that, you can have a very simple 2-pointer approach where you can start with, let's say, assuming, let's say you have already sorted them, and let's say these are all sorted. So what I can start with is this first guy, then maybe figure out that, okay, this first guy, where does it intersect with? If let's say this intersects with this guy and this guy, then I skip. And then I move on to the guy over here, that is L4, R4. And I'll count this, and then my pointer is at this location. Then I keep on doing this, whether the intersections do happen or not. And I move on, counting only those particular segments which did not intersect in them. And I did that greedily, so I will definitely end up with the best intersections, with the best segments rather, which did not intersect, overall maximizing my count. Okay, so this is the problem. Let us actually try to dry run this on the case, so it would be much clear. A, B, C, D, E, A. So I have A, B, C, D, E, A. Then F, D, E, F. I'll mark the indices 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, now where is A coming? 0, and it's coming at 5. Where is B coming? It's coming at 1 only. Then where is C coming? C is also coming only at 2. When is E coming? E is coming at 3 and 8. Where is D coming? D is coming at 4 and 7. Okay, so I'll write 4, 7. Now where is E coming? E is coming at 3, 8. F is coming at 5, 9. Great. This is done and dusted. Now let me extract the segments from this. Okay, so from A, if I go to A over here and I'll standing at 0, I need the best guy, which is 0 plus 3, greater than 0 plus 3, which is 5. So that means 0 to 5 is a segment. I can push it. So I know that in my segments area, I'll be pushing 0, 5. Okay. Now B doesn't actually create any segment. Of course, you know that you also cannot create any segment that starts with Y because there is nothing after 5. So that is done and dusted. So A only gives me 0 to 5 as a segment. B doesn't give me, C doesn't give me. Now E does give me. E gives me 3 to 8. Similarly, I think I can say that D also gives me that. That's correct. Now, greater than equal to, or rather 4 size overall. So this is like 4 and 7 over here. So I know this can make stuff for me good, right? So I can note this down as a segment. It's like 4, 7 over here. Then I have 3, 8. I think I already took that. And then I have 5, 9. Okay, this is good. Now I have these 4 segments rather with me. I would sort these segments. When I sort these segments, they would actually look exactly like this. This is going to be the first segment. This is the second segment. This is the third segment. This is the fourth segment. Now I want the maximum number of non-intersecting segments, which is very obvious. If I start with this first segment, this actually intersects with 2 and also with 4. So I will cross these 2 out. And it doesn't intersect with, it intersects with 2 and the third segment. It doesn't intersect with the fourth segment. So I'll count the fourth segment. And I was already counting the first segment. So overall segments that did not intersect, they were 2. And they actually denoted that there is a substring from 5 to 9, which is this one, and a substring from 0 to 5, this is this one. So yes, you got the answer, you got the correct value. Okay, so I really hope this problem is clear to you. We can now jump to the code part and see how do we actually implement this out. All right, so here is the code. I will take the size of this word, that is n. Then I have n less than 4, I of course return 0, no brainer. Less than n size, 4 size, then I know there are no substrings. That would be nice. Then I have this map of integer of vector of int of pos that is basically trying to map against each and every character where are the ending, the positions rather where it occurs. So I'm maintaining integer in terms. Why? Because I can simply have ASCII indexing over here. I'll go to each and every letter that is in word of I. Word of I minus small a will give me the value. So 0 means A, 1 means B, 2 means C, and so on. And then I push back I in this. So corresponding to every letter, I basically get those, get that vector which dictates that where does it all occur, right? Then I have this intervals, which is maintaining all the L, R's. I go to every, you can say A in this pos, that is the map. Then I would want to iterate in the A dot second, that is the vector itself. So I go from 0 to A dot second dot size. Then if let's say I have A dot second of K right now with me, then A dot second of K plus 3 is something that I need. Okay, this is like greater than, I think I must have said in the previous explanation, greater than this part. I think that was wrong. Ideally, that should have been greater than equal to 3. So I'm so sorry over there. I must have mispronounced that part. This is ideally very obvious. In your mind also, this should be very clear that if you're standing at some index that is A dot second of K, then if that, let's say, index is 4, then 4, 5, 6, 7. So that's like 4 plus 3, that's 7. So you basically want greater than equal to 7. That's A dot second plus of K plus 3. That's the needed thing that you want. So now you can lower bound this part in this particular basically A dot second vector from the begin to the end with this need value. And now if this lower bound returns to you an iterator which is not equal to the end, then you know that you have actually received this R. So if this was L, then there is an R. Now, sorry, if this was L rather, a dot second of k was L, then you have actually got that this IT, this index is that particular R. So you need to push back this particular index, and that index dereferenced, of course, this is an iterator, so star of IT as an L comma R pair in the intervals. Now, once this is done, you can imagine that this is going to happen for all the letters. For A happens, then B, then C, so on till Z. Now you can sort them. What is the sorting thing that you want? You want that the second values are in increasing order. The smaller second is preferred. So you can say A dot second is less than B dot second. That is the custom comparator you can say I have called over here in the sorting function. And then once that is done, you need to figure out that, okay, what is the maximum number of non-intersecting segments? Classical problem, take some sort of a answer variable that's 0. Last end, that's the R part. What is the last R that I took in this particular section? I have -1 initially. I will iterate in the intervals. Now, if it dot first is greater than last end, that means I've actually entered in a different segment. So answer becomes ++, and I'll say, okay, last end is equal to it dot second. And this for loop finally ends out. And when this ends, I have the answer variable giving me the non-intersecting segments from this intervals vector. This is the correct answer. Okay. Now, what is the overall time complexity? I am using a map over here. So that's like log n extra. So this is like n, and then this is like log n. Okay. Insertions. Then this is like iterations. So you can say maximum, this is like 26 iterations that is happening over here in the POS map. Then this is maximum size. So this can be like n order again. That's a very high bound over here. Then this sorting is going to have n log n. Okay, this is like n log n. And then this intervals is like n order maximum. So I can say that I have actually come up with something like O of n log n to be the overall complexity. Now n is in 10 power 5 order or 2 into 10 raised to 5 order. So this means this is like approximately writing O of 10 raised to 5 into like 30, something like a 10 raised to 6 order is what I have. And what is the space complexity? That is O of n, that's coming from the map. So I have, or the string also rather, and from the map too. So I have actually gained a solution that is n log n, which is making sense for orders of 10 power 5. Linears or linear into log is something that normally works. And this is the whole problem. This is greedy problem overall, implementation plus greedy. So your knowledge should of course be how do you figure out non-intersecting segments? How do you handle maps, vectors, and so on stuff? Probably how do you use lower bound very nicely, which is very, very easy to actually understand and do. It's very crucial to also understand that when I took this logic or was discussing this, I did not mention lower bound. So I took it right and right over here. You could of course answer why lower bound, because I want a very neat time complexity. Actually, I think I did not take the time complexity for this part also. This is like log n more. So this is like 26 into n into log n. 26 is almost constant. So you can write this to be like n into 26 only. So maybe you can roughly take this as a 10 power 7 order sometime, but that is also fine. Like overall, I can say that this is like 26 into n into log n, which is like 10 power 7, 10 power 6 order. Everything works. Now lower bound is very, very nice because this is going to get me in a log n order the need thing that I want. And from the need, the index that I want, that is at +3. But if I would have used some sort of a linear iteration over here inside this, then that would have been something like n into n, that's a square order, which would have not worked. Hence lower bound. Hence when I was discussing this problem, now I think you can understand why this implementation works. All right, this is all. Let's move on to the third problem. All right, so problem number 3, number of ways to assign edge weights 1. So this is the first problem of this category. Then the fourth is actually the second part of this. Let's see this. There is an undirected tree with n nodes labeled from 1 to n rooted at 1. The tree is represented by a 2D integer array edges of length n-1, where edges of I is basically ui to vi, indicates that there is an edge between nodes ui and vi. Initially, all the edges have a weight of 0. You must assign each edge a weight of either 1 or 2. The cost of a path between any two nodes u and v is the total weight of the edges in the path connecting them. Select any node x at a maximum depth. Return the number of ways to assign edge weights in the path from node 1 to x such that the total cost is odd. Since the answer may be large, return it modulo 10 power 9 plus 7. Okay, so this is a very, very simple problem of tree. Okay, let's try to understand this very quickly. You will be given, of course, a tree structure that looks or may look some anything. I'll take a very simple example. Let's say this is a tree. Okay, this is like the root node. Then you have like 2 more down here, and this is the structure. Now in this structure, what is your first task? Your first task is to basically choose the node 1, which is very obvious, the top node. It's the start or root of the particular tree. And then you have to choose a node which is basically at the maximum depth. Now there might be n number of nodes which are at the maximum depth. You can choose any one. So over here, it's very obvious. I can see this node is also at the maximum depth. Now, by the way, sorry, what does depth mean if somebody does not realize this? Depth is basically the distance as you come down from the node 1 right to the very bottom. And the maximum depth is the maximum of that. So I can say that this node is at a depth of 1. This is at a depth of 1. This is at a depth of 2. And this is also at a depth of 2. So what's the maximum depth in this? Of course, it's very, very simple. MD, maximum depth, is 2. And what are the nodes which have that depth? This is the node, this is the node. So you can pick up any node. It really doesn't matter which node do you pick up. You, let's say, pick up this node. So I'll say this is blue and this one is blue. So I have picked up the two nodes which have the maximum depth, which is 2. Now what's the next thing we want to do? We want to see what is the path that connects these two nodes. I'll pick up that path. This path basically is this one. Next, what I'll say, okay, what are the number of edges that come in this path? There are 2 edges that are coming in this path. And these edges right now have not been allotted any weight. So what is my target? I have to allot these 2 edges in this path a weight of either 1 or 2. A weight of either 1 or 2 such that the sum of weights I declare on this path end up to be odd in nature. Okay, odd in nature. So there can be different ways to do this, as in maybe I'll give you a very small example. If let's say I allot 1 weight over here and 2 weight over here, then the sum is 3. What is 3? 3 is odd in nature. Maybe I could have allotted 2 over here and 1 over here. Is that also not 3? Yes, that's also 3. So one way was 1 over here, 2 over here. One way was 2 over here, 1 over here. So don't you think there are 2 ways? And there could have been more, right? Had the path been longer, more paths, more ways. So that means I know I have found that the solution to the problem is basically figure out this number of ways to allocate the paths 1 or 2 weight such that the sum of them is odd in nature. Okay, now that is going to be some x number. That x number might be large also. So that's why they have actually told you return this modulo 10 power 9 plus 7. So if that number is x, I need x modulo 10 power 9 plus 7 just so I don't overflow. This is very standard way of presenting answers. Okay, I hope the problem is clear. Give it a 2-minute thought. How would you solve this? Probably see these cases. I think I've taken the test case number 2 rather over here to explain this idea to you. And the answer was 2. You can easily check this out. Okay, once that part is done, let us actually move on to the solution of this problem. Now this is again, as I said, a very easy problem because intermediate level, the only thing that is there is the concepts, but the implementation and the idea to think if you know those intermediate concepts is a cakewalk. You basically have some tasks in this. First task is figure out max depth, either the node or the max depth itself. Actually, both will work in this case, or rather even the just max depth number will work in this case. Why? Actually, I'll tell you. But let's figure this part out. I think this should be very clear. You need to figure out the max depth, right? You need to know what is the max depth of this tree from 1 to whatever node that you have. Okay, and what's the next thing that you want? The next thing is you need to figure out some sort of pattern or combinatorics to actually determine that how do you calculate this number of ways, right? How do you calculate this number of ways? If you're able to do that, some combinatorics for ways. If you're able to do that, this is all that is there in this problem. Now the first part is really very easy. You just need to figure out a very simple traversal technique for this tree. Any popular technique like DFS or BFS will work. You can, I think, preferably go with BFS. So start with node number 1 and try to figure out the depths of every particular node. And when you of course reach the very last of the nodes, very leaf of the nodes, they will have the maximum depth. So you can have some sort of a max depth variable, which is basically maxed out with the current depth that you are on right now. And when you come out of this whole BFS or a DFS traversal technique, you will be able to get that max depth. That's very clear. Now, why am I saying is only the max depth is needed? Let's try to figure that part out. Okay, let's take this diagram over here. Let's say that the max depth is 4. That means basically you can imagine there is a node 1 and then there is some node at the very end, and there are basically 4 edges in between it. Correct? Is that very right? Yes, there are 4 edges. Max depth MD right now is 4. Now I want to allocate them some weight. That weight can either be 1 or it can be 2. Only condition is their sum should be odd. Now pause for a second and try to understand, when is a sum odd? See, when you have some current sum S and you add 2 to it, if this becomes S dash, then the problem, or rather the observation over here is, the parity of S and S dash is same. That means if S is odd in nature, then this also remains odd. If this is even in nature, this becomes even. But if you actually add 1 to it, and this is new S dash or S double dash rather, the parity is reverse. If you have odd, this becomes even. If you have even, this becomes odd. Now actually I can use this property. How do I use this property? See, when you allocate 1s or 2s over here, my claim is as long as number of 1s is odd, the sum is odd. Why? See, the sum right now will start with 0. Maybe you allocate some 2s to it. Maybe there are some edges which you make the weight to be 2. So it will become plus 2, plus 2, plus 2, so on. But whatever this final value lands up to be, it will still be even, because 0 was even. So this will also be even. Now after this, you have an even number. When you add plus 1 to it, it will become odd. When you add plus 1 to it again, it will become even. When you add plus 1 to it again, it will become odd, and this reverse chain will actually follow. Which means if you land or want to land at an odd sum, you only want to add 1 odd number of times. See over here, when I added 1 only 1 time, it was an odd. If I would have added 1 3 times, it was again an odd. If I would have added 5 times, it was again an odd, which clearly means that I have observed that 1's count has to be either 1, 3, 5, 7, 9 and so on to actually figure out what is the odd sum. So if example I have 4 edges to basically allocate these weights, out of these 4 edges, first I can see how many edges, or what are the number of ways, do I get when I actually allocate only one edge, any one edge, a 1 weight. So that's out of 4 selecting any one edge, so that's 4C1 plus. Now the next thing is, if I would have allocated 3 edges the 1 weight, any 3 edges, what is that? Out of 4 edges, select 3 plus this goes and goes on. If I try to generalize this formula, this actually lands up being a very neat formula. That is, if let's say there are n edges, okay, if let's say there are n edges you have, then this will be nc1 plus nc3 plus nc5, so on, so on, so on. And this is what exactly, this is actually a very popular sum that comes from binomial theorem, okay? Binomial theorem. You can pause the video and actually cross verify this on Google. You will actually see why this formula lands up being exactly the value 2 power n minus 1. That means if there are n edges, then 2 power n minus 1 is this sum. So that clearly means that if I actually want to figure out the answer after I've calculated the depth, if let's say in this case I have calculated the depth to be 4, then the answer, that is the number of ways such that I allocate 1s and 2s, in this case rather only 1s in my thing because I want odd nature to come from it, I'm really not bothered about the 2s, is simply 2 power 3, which is actually going to be, 8. Yeah, this is the correct answer. Okay, and this is going to work. How? Let's go back and see this case also. Over here also I said the answer was 2. Why was the answer 2? The maximum depth that you calculated was actually 2. So you basically calculated 2 power md minus 1, so that's 1, which was 2. So yeah, the answer turned out to be 2. You had 1, 2 or 2, 1. Simple. You can actually pause this video and see if this cross verifies. This will cross verify. You just basically need the maximum depth, and then you need to calculate maximum depth, 2 power maximum depth minus 1, and that's done and dusted. So this is the problem. Can you see how simple this is now? You have just one BFS call to figure out the max depth, And really a very simple combinatorics logic to figure out 2 power md minus 1. Now, why is this medium? Why is this problem medium? Because the logic is very clear, right? What do we want to do? You must have figured this out probably within 5 minutes. But to do this, you need some concepts. First of all, you need, as I said, BFS. That's not beginner friendly. Then you need some combinatorics to understand this formula. Again, not beginner friendly. And one more thing that is there, you cannot actually overflow. That's why they have return it modulo 10 power 9 plus 7. So you need to do this 2 power md minus 1 and return modulo 10 power 9 plus 7 following all the arithmetic modulo operations, all these rules that we have in arithmetic modulo. That means you again need that knowledge of how does modular arithmetic works in this case. And only when you have these 3 items in your set, only then you can solve this problem. So if you actually attempted this problem, figured out the logic, but was not able to code it up, make sure that you cover these topics from somewhere else, some other resource, and come back over here and then try to attempt this. I'm really sure you will be able to solve this problem. Okay, so this is all that is there in this question. Just figure out MD and print 2 power MD minus 1 modulo 10 power 9 plus 7. Let's actually move on to the coding part and see how do we implement this out. Okay. So what I've done over here is I have taken, of course, mod value, that's 1e9 plus 7. Then I have a vector of power of 2, which is basically powers of 2, moduloed out with 1e9 plus 7. I would be using this vector so that I can actually fetch quickly the value which I want. You can, of course, avoid this by taking a single value, but I'm doing this because I was trying to copy paste my code in the second part of this problem. That's the fourth problem. You will see how, but let's continue over here. Now, what have I done is I've taken, of course, n, that is edges size dot size plus 1. Why? Because there was edges array to be n minus 1 size and there are n nodes, so that's basically the size plus 1. Then I've created an agency matrix. I push back u and v in this. I, of course, small pointer over here, maintain the 0 based or 1 based indexing. Make sure that you don't break this code or you might run it into array out of bounds. And after I have made an agency matrix, I have the depth vector, I have a queue. I'm using a very simple BFS sort of an algorithm. The depth of 0th node, or the first node in this case, if 0 based indexing is done, is 0. I push back 0 in it. And then I actually first calculate the powers of 2 basically. So I resize it to be n. 2 power 0 is 1. And then I basically have this loop. How do I actually calculate this? It's really very simple. If you have 2 power, for example, if you want to calculate in this case, what is happening over here? If you want to calculate, let's say 2 power 3, then 2 power 3 is basically 2 power 2 into 2, right? So I have calculated, I would have calculated power of I minus 1 already. And I can just make sure that I move it left shift again by 1. That is basically doing into 2 and taking a mod again. So this follows the modulo operations and then I get 2 power I. And this goes on and goes on because finally 2 power max depth minus 1 is what I want. So I'll get that value. Okay. Simple, neat. Now I have the max depth variable, which is 0. I run a BFS logic and I basically pop the front. Then I use the depth of that to be max depth out of my variable. Then I go in all the children of this agency of this node rather from the agency matrix. If the depth has not been yet traversed, if it's still -1, that means I can make its depth to be the depth of its parent, that's u, plus 1, that's the new child's depth. Very, very simple. And then I push back this child in it. When this while loop ends, the BFS calls are made and max depth stores the maximum depth. Then all I want to return is pow2 of max depth minus 1, that is 2 power md minus 1 that I told you. And this is calculated by modulo operations only, so you can directly return it. This is definitely the right answer. All right. So this is the whole problem. Really, very simple. What is the time complexity now? This is like edges vector, so this is like n order. Then this is also n order to calculate the power thing. Now this is, you can say, a BFS call, which is like n plus m, where m is the edges, n is the nodes. Now in this, n is the edges, and n minus 1 is the, n is the nodes and n minus 1 is the edges. So I can simply say this n plus n minus 1, which is like 2 into n, which is like n only. So I can say this is n order again. And then this is pretty much constant. So I have actually calculated the whole time complexity to be O of n, and the space complexity is also O of n. Okay, now what is the n in this? This is 10 power 5. So this works out. This is like O of 10 power 5 order. Really very good. Definitely works out in this complexity, and same for the space. Okay, so I hope the problem is clear. Let's quickly move on to the second part of this and we'll see how do we use these ideas in the second part also. Okay, so the final problem. Now this is exactly the copy of the last problem. There's a very small difference. You are doing the same thing. You want to assign the edges weight 1 or 2. You're trying to figure out if the cost of that path is odd. just in this part, there is nothing like saying you are going from the node from you can say 1 to some x which are at the maximum depth. Basically, you have a queries sort of extra vector that is given to you, which gives you from which node to which node do I want the path that I'm considering, and then tell me how do you figure out the number of ways to assign edges in that particular path such that the cost between that UI to VI node is odd. So this is this extra thing that are given. Now they're not restricting you to 1 to x where x has the maximum depth, but any random nodes you pick up. You might pick up 2 to 5, you might pick up 4 to 5, you might pick up 1 to 5, anything, anywhere from anywhere, any source to any destination. Okay, rest everything is same. Which is why now this problem introduces a new complexity that you really cannot do any brute solution anymore. You cannot go for actually going to every query and figuring out what is the path from this particular source to the destination, and then let's see that, okay, how do I figure out what's the depth now, maybe, the length of that path now, and then maybe calculate that with like a 2 power md minus 1 sort of a logic that I used in the last time. That is all not going to work. I mean, not completely, because you actually don't want to calculate this path every time. You cannot do that. You just cannot go to queries and do this part. Which is why I need another, you can say, topic in my quiver of arrows over here so that I can actually use that to solve this problem. Everything else is basically the same. Okay, so let's try to discuss this problem. Let's say that you have the same tree. Okay, I have the same tree. It looks like this. Let's pick up the node that is over here and the node that is over here. Now the path that I'm talking about is this. This is actually the path. Now there are 3 nodes in this, 3 edges in this, 1, 2, 3. Now you can see that there are 3 edges, right? For now, let's assume that you somehow got to know that yes, there are 3 edges in this. Then can you actually use your previous problem's idea to get the answer for this? You can do this part very easily, right? If you know that this length is 3, then you just need 2 power 3 minus 1, that is basically 2 power 2, which is 4. So there are 4 different ways to allocate these edges 1 or 2 weight such that the sum is actually odd. And that is something like 1, 1, 2, not 1, 1, 2, 1, 2, 2, 2, 1, 2, 2, 2, 1, and 1, 1, 1. These are the 4 ways. So if somehow you get this particular value, that is this guy over here, this 3 over here, then you know the answer. Yes, you know you can calculate using the same idea in the previous problem, but how do I get this 3? I of course said right now you cannot traverse from this to this. You cannot do that part because there are Q queries like this, so you cannot do that. How do I tackle this problem? Now I'll show you this with a very, very simple diagram. Let's try to observe the main root idea in this. This is the tree. Okay. This is node, and this is the path. Now this path is actually going through a very special node, which is actually this node. No, this is not special because it's the root, but rather it's special because this node in its virtue is called something as LCA. That's the least common ancestor. What is least common ancestor? You can pause this video and actually search Google once. I'll give you a very brief definition. Least common ancestor is the node from, like, if you want to calculate the least common ancestor, it's calculated between 2 nodes. In this case, this is node 1, this is node 2. And the least common ancestor means that if from this node I'm going up and from this node I'm also coming up, what is the lowest heighted node from, or rather the highest heighted node from the top, where these 2 paths actually intersect, which have the same ancestor, the common guy. This is called the LCA. Now, this LCA is very, very important over here. Why? Because imagine that if you have the height of, or rather the depth of the node number U from the LCA, you also have the depth from the node LCA to this other node that is V. And in this case, it just turned out that this node was in itself the root. But you can imagine that maybe this had one more root above it. Maybe this was the root guy. I'll extend this rather. If this is the root, so I'll say that this is the height rather. For U, from the root, this is the height. Not from LCA. I'm so sorry. From root, this is the height. For the node V, I'll do it like this. Let me rub this part. From V, this is the height. And the LCA nodes, the green nodes height is this much. Okay. Now if I tell you, you have to figure out the path length. You just need the length, right? You just need the path length from u to v. What is it? See, this length is 2, this length is 1, and this length is 3. The very simple formula is, if I add the two depths of u and v, that is, if I add up d of u plus d of v, and I subtract 2 into d of LCA, then I basically land up with that path length. D of v, d of u, that is 5, minus 2 into 1, that's 2, this is 3. And voila, 1, 2, 3. 3 was the path. Just pause the video and think this diagrammatically. Why is this working? It's very simple to think. It's working because you basically are having this as the depth, this as the depth, and then you are subtracting from that two segments, two parts coming same of the common path from this and this. And that's why this was the remaining path which you calculated, you got the length. Okay, now you have now figured out that you can get the length if you know the LCA. But how do you know the LCA? Do you again need some sort of a BFS logic? Do you again need some sort of a DFS logic? No, I actually don't need that. This is where another set comes into picture, another problem set comes into picture, topic comes into picture. It's very commonly associated with LCA, that is, how do you calculate LCA very quickly? It's by an algorithm called binary lifting. Okay, this algorithm binary lifting is really very fast. This actually returns to you the LCA of two nodes u comma v in log order, where log n is like n number of nodes. Now, how is this fast? Think of the complexities now. See, imagine that I run a loop that is for the queries outside. Okay, that's for the queries outside. And in this query, I basically am standing at, let's say, ui and vi. Now, I will first ask you, what's the LCA for this? You will say, okay, I'll call some function, I'll get the LCA. This is going to run only in log n order. And after I have calculated the LCA, I have already pre-calculated the depths, because I know I am only fixing my depths from the root guy. So this depth is there with me, this depth is there, this depth is there. So I can quickly get this part also. And then I just need to figure out 2 power 3 minus 1, which is very, very easily possible, because remember, I had calculated a power 2 vector, which was getting me all the values. If I would have calculated power of I, power 2 of I, that's basically 2 power I. So I can easily calculate 2 power I also. So if I do binary lifting, I will actually end up with a logic where this outer loop will be running in queue time. This will be running, as I said, log n time. Then to calculate the path length, it would be almost constant time only. Okay, almost constant time. And to calculate this 2 power I, that's also pre-calculated only. So your answer will also, for this particular ith query that you have, will also be constant, O of 1. So you basically have ended up with some sort of a complexity that is q of log n. This is again for the queries part that I'm saying. There is going to be some time complexity that comes from the pre-computation of binary lifting, and some computation that comes from this 2 power I calculation, right? This depth calculation also, this 2 power I calculation. So all these parts can be pre-computed. Okay, pre-computed. And once they are pre-computed, I know that I have actually come up with a very neat and a very good logic. Again, this problem is no rocket science, okay? Binary lifting is a very, very common topic that is often seen in Leetcode 3rd and 4th problems. If you're very new to Leetcode, I would advise you that you read binary searching. If not, you know what I'm talking about, right? You know, you can comment in the chat, yes to this part. You have seen binary lifting endless number of times in medium to hard problems of Leetcode, if it's related to a tree. So this is no rocket science. It's very easy to figure out that, okay, I needed LCA. And the best way to calculate LCA is by binary lifting. I can just take a very boiler template code over here to calculate binary lifting, and I'll actually be ending up with the answers very, very accurately. This is all that was needed in this problem. Okay, so that is all that is there in this problem. Let us quickly discuss the coding part and see how did we optimize basically sort of problem number 3 to 4. Okay, so over here I have the whole idea. I have this DFS call and this this extra calls of like the up vector, a vector, the depth vector, pow, the G, that is the graph or the agency matrix. Then this is basically a boiler template code to calculate binary lifting. This is to calculate the LCA, and no need to I don't need to go into the very depth of how this works. You can again pause the video and see binary lifting as a separate topic. And otherwise, you know that this is a boiler code. What is the main idea rather? You of course have the n, that's edges.size plus 1. Then you have this log 1 variable, which is basically in binary lifting what we try to do is we try to figure out what's the logarithmic value, closest upper bound logarithmic value of the n number of nodes. So I calculate that, Then I calculate the agency matrix, really simple. I calculate the up, that is a very important vector, a vector used to actually do the binary lifting part. The depth, which is again the same code back from there. A DFS call, which is how do we actually end up calculating binary lifting. Then I have this particular code, which is actually the same code I used from the last problem. If you remember, very simple, calculating pow2 by this mod part. And then I have the answer vector. Then I actually reserve some space for the answer in the query size. And then I run to every query. I have u as q0, v as q1. If both these nodes are same, if you're basically calculating the path from a node to a same node, then that's answer 0, continue. Else, I figure out the LCA. And what's the length of that path? That's depth u plus depth v minus 2 into depth of w. That's the LCA. Then I simply push back 2 power L minus 1 in my answer. That's pow2 calculating of L minus 1. And I return the answer vector. So I have actually calculated everything very, very quickly. What is the time complexity? Okay, simple paths. This is like n order. Okay, this pow function, this is also like n order. Now this is a DFS call. So this roughly you can see this works in like a log vector over here. This is again the main thing. So you can understand that this is some sort of a DFS calls of how normally on tree looks like. So this can also be estimated to have an n order again. And same thing, this is Q. Now this LCA calculation is actually log n. Why? You can actually see this code over here. In the code, we are actually working with log values running as a loop, and log is basically log of n. That means we know that this is roughly a log n order. So this is log n, as I explained, this is constant, and this is also constant. So I have come up with a complexity that is best case something like n plus q log n. And what is the space complexity? That can be estimated like a n order only, considering I have the agency matrix, the depth call, the vector call over here. It can rather be written as n into log n as a better depth, but then this is just really fine. N into log n is also not very large. I mean, space is not a big problem over here. Now 10 per 5 order, does this work? 10 per 5, 10 per 5 queries, this works because this is 10 per 5. It's like writing 10 per 5 plus 10 per 5 into log of 10 per 5, which is something like 30-40 iterations. So this is like really, really good to go, really fast. All right. So this is the last problem, right? As I said, this was very, very easy. Why? Because the logics are cakewalked, right? The whole contest, the logics were really cakewalk. It was just learning about these topics. If you don't know binary search, you will not be able to attempt this problem. I can guarantee you this part. But if you know binary search, this is one of the easiest problems on binary search. This is, I'm so sorry I was saying binary search. Binary lifting. If you know binary lifting, this is one of the easiest problems on binary lifting. Hence, you know that, okay, if I know this topic, it's a cakewalk. That is all that is there. Okay, so this brings us to the end of this post-contest discussion. I hope you like the problems. I hope you like the solutions. If anything, do drop in the chat and I'll make sure that I try to reply back to the doubts and queries. Thank you so much for watching. That is all.